Hey everybody, it's Mr. Carr again. Today we're going to be looking at 9-1 day 2. What we did was we started with our initial polar coordinates. Now we're going to talk about simple polar equations that are based on that. Okay, so let's take a look here. Graphing our polar equation r equals 2.5. Think of r being basically a radius. So if I think about it on here, we're trying to represent all the possibilities where r is equal to 2.5. And there's a lot. So obviously on the polar axis, we can go right here. That's our first spot, but I can also go anywhere I want as long as it's at 2.5. Well, look at what shape we're creating. If I just keep going around and around and around, I'm basically creating a circle. And that's what this is. R equals 2.5 is a circle with a radius, whoops, radius of 2.5. So I'm gonna go ahead and draw that in now. And oh, that didn't quite work. Let's try that one more time. Draw my circle in, and boom, there we go. Perfect. All right. So that's r equals 2.5 is just going to represent a circle like that. Theta equals 5 pi over 6. Now, because this is my almost like basically my input, theta equals 5 pi over 6. If I look at where that degree, where the radians is, that's right here at 5 pi over 6. Okay. So that means it is going to be on anything that's on here. So if theta is equal to that, it's anything on there. So I'm going to just draw that as a straight line. Okay. But remember how we did with our coordinates. We can also represent the rest of the line as being what's opposite that on my polar circle here. It's all of this. Okay. So that means my theta equals pi over 6 is a straight line that can basically connects 5 pi over 6 to 11 pi over 6. It's the other half of the circle then at that point on that side. So let's continue with our work of finding with our polar coordinates. We're going to look at what's called the polar distance formula. So if P1 and P2 are 2 points that are on the polar plane, their distance is given by this equation here. Notice, that's here. Let me say the distance is equal to this. Okay. So when you do this, first of all, let me point out here. Notice how it's value squared plus value squared minus 2 times each of the values times the cosine of an angle. This is basically law of cosines. If I want to find the distance between these 2 points, look at what I can create when I make a radius going from here. So here's R1. Oh, come back here. Right there. There's R1. And then here's R2. And then the angle in between is being represented by this. Okay. If I take theta 2 minus my theta 1, that's going to give me this angle inside. Okay. So that's how we're finding this out. So let's look at our first example here. An air traffic controller is tracking 2 airplanes that are flying at the same altitude. The coordinates of the planes are at 860 degrees and B is 300 degrees, where the directed distance is measured in miles. Sketch a graph of the situation, and then let's find out how far apart the 2 planes are. So let's start with modeling our 2 planes here. Plane A is at 860 degrees. So 60 degrees is right here. So if I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. So from basically we're saying from the airport, which is right there at my pole, it looks like that. So here's A. B is at 300 degrees and 4. So that is going to be 300 degrees is right here. So I go 1, 2, 3, 4 right there. Okay. And what we're trying to find is this distance to go from A to B. Okay. Again, we've done this before. It's a triangle, but let's use our new formula for this. So if R1 is equal to 8, R2 is 4, then theta 1 is 60, and then theta 2 is 300. Okay. So we're going to go distance is equal to the square root. All I'm doing is my distance formula. So it's going to be R1 squared plus R2 squared minus 2 times R1 times R2 times the cosine of this difference between the 2 angles. So 300 minus 60. Okay. So distance is equal to the square root of, this will be 64 plus 16 minus, we got 2 times 8 times 4 is going to give me 64 times the cosine of 240. So if I do that, I'm going to get about 10.5, whoops, got ahead of myself, 10.583 miles here. But we can still do this with our officially law of cosines, because this angle here is definitely not 240 degrees. So how does this work out this way? Well, let me do a second version of this. Let's figure out what this angle here, this included angle is. If I look at going this direction here, right, that's my polar axis. I can go this way is 60, and I go this way, which is also 60. So my angle in between is going to be 60 plus 60, which is 120 degrees. That's my included angle. Okay, so I'm going to try the same thing again with just law of cosines. So the law of cosine says it'll be the same idea. It'll be like a squared plus b squared. So that'll be 8 squared plus 4 squared minus 2 times 8 times 4, whoops, times the cosine of 120. Okay, I'm running out of space here. Let me move stuff around so it's a little easier to see. Do that there, and we'll do this one right there. There we go. Okay, so times the cosine of 120. So again, if I plug this in my calculator, calculate this all out, this actually comes out to the same exact thing. Okay, thanks to our periodic nature of like sines and cosines, cosine of 240 ends up being the same thing as the cosine of 120. Okay, so that's why we get the same answer either way. Notice that everything else is the same. Okay, so that's actually it for today. So if we look at our special case scenario, we're looking for the distance between 2 points on a polar grid. We do that with our special formula, which is basically law of cosines. All right, but that's it for today. Take care, everyone.